Hi, this is Joseph Arbizu. I'm a math guy over here at Armio, and we're going to help you out because some of you guys come up to me and say, I don't get it. And I'm going to help you get it. So let's start. So today we're going to work on how to model linear situations. So make sure that you have your skills practice book. We're going to be looking at section 2.1. I know it's upside down. Don't worry about that, sweet babies. I want to fix it for you in a quick second. As I said, we're going to practice how to model linear situations. I'm going to show you about the independent and dependent quantities of a scenario. I'm going to tell you how to fill out a t-table given a scenario where we're going to determine independent quantities and dependent quantities along with their associated values. I'm going to go and talk about function notation really quickly, and then we're going to finish it up with evaluating particular values given a function. How does that sound? Good. Okay, so we're going to start out with problem number 2 actually. Problem number 1's already done. The instruction says that we're going to identify the independent and dependent quantities. Let me highlight that. The independent and dependent quantities in each problem situation. Then we're going to write a function to represent the problem situation. So let's take a look at problem number 2. It says that Sophia is walking to the mall at a rate of 3 miles per hour. So given this context, even though they don't tell us anything about the time, the independent quantity is going to be time. So let me write that. The independent variable or the independent quantity is time. And then after a certain amount of time, she's going to have traveled a certain distance. Let me see. It says that she walks 3 miles. Man, she walks fast. The dependent quantity is the distance. Dependent quantity is distance. So let me make sure that I know what's going on. If she walks 1 hour, she will have walked a total of 3 miles. If she walks 2 hours, she will have walked a total of 6 miles. So over here we got time, and this is going to represent distance. So what's a nice way to figure out how much distance she will have traveled after a certain amount of time? If I don't know how much time she has traveled, t, whatever that value is, what do I got to do? All I got to do is multiply by 3. So if the time is t, I'm going to take 3 and multiply it by t, and that'll give me the amount of miles that this person has walked. So if you want a function, we've got it. The distance after a certain amount of time is equal to 3 times t. Now, some of you guys are going to try to be fancy, and that's fine. Another way that you could write this, but if you're going to do the fancy method, make sure you take that pinky out, stick it out. Look at it's right there. The distance after a certain amount of time, pinky out, is 3 multiplied by time. And that's done. This is my function for this situation. I'm going to put a nice box around that. Let's look at number 3 real quick. All right, on to number 3. Mario is stuffing envelopes with invitations to the school spring carnival. He stuffs 5 envelopes each minute. My brother stuffed envelopes at PG&E. This is an important skill. Let me see. He's stuffing envelopes with invitations to the school spring carnival. All right, I got that. He stuffs 5 envelopes each minute. What's the independent quantity? It's time again. So I'm going to write independent quantity. Independent quantity. It's time. I know that if Mario is stuffing envelopes for 1 minute, he's going to have 5 envelopes stuffed. So the thing that relies on time is the number of envelopes that he's done. So the dependent quantity, because it relies on time, that's what dependency means, is going to be the number of envelopes stuffed. Envelopes. You got to spell, I'm in front of an English teacher. Envelopes. All right, stuffed. So let's think about this. We got to think about a function. I'm going to write this a little bit different. We're going to have time over here, and we're going to have envelopes stuffed here. So let me see. What's a good unit for time? Is it in hours? Is it in nanoseconds? No, it's in minutes. So after 1 minute, how many envelopes will you have stuffed? 5. After 2 minutes, how many envelopes will you have stuffed? 10. After 3 minutes, how many envelopes? 15. You guys get it. After 10 minutes, this guy will have, let me see. How do I figure this out? 1 times 5 is 5, 2 times 5 is 10, 3 times 5 is 15, 10 times 5 is 50 envelopes. So the function that we're going to use to represent this, if we don't know how much time t has gone, all I got to do is take t and multiply it by 5. So my function is going to be the envelopes is equal to 5 multiplied by time. And I'll write that like this. Check it out. The envelopes after a certain amount of time is equal to 5 envelopes multiplied by each increment of time, where time is in minutes. Let's go on to the next set. Okay, so you guys are going to have to do problems 4, 5, and 6 on your own. I'm going to skip over to problem number 8. This is on page 263. Number 8, it says that Jada is walking to school at a rate of 2 miles per hour. Is that fast or is that slow? That's fast for me, man. I'm a fluffy dude. Jada is walking to school at a rate of 2 miles per hour. What's the independent quantity? It feels like it's time again. So I'm going to put time. What are the units for these increments of time? Well, they're talking about miles per hour, so the units are going to be hours. Now, what's being affected after a certain amount of time? It's her distance. And the distance, I am going to use, let me see, what unit? She's walking 2 miles per hour. It's not 2 feet per hour. It's not 2 yards. She's going to be walking miles. Nice. What's a good variable or a good expression to represent time? T. That's nice. T for time. What's a good variable to represent distance? D or M? I'm going to use D. Like touchdown. Get it? All right, so let me see. Oh, you know what? This isn't right. The distance, well, it is good that I got D, but let's see. The distance, if I have a certain number of time traveled or time gone, I need to take the mileage, which is 2, and multiply it by t. So this is, I think this is the expression that these people are looking for. If I take the time and multiply it by 2, that'll give me the distance in miles. So let's see what we got here. Man, that's hard. I don't want to do that. I don't want to do that. Ooh, the number 1. I know what that is. Let me see. If the distance is 2 times 1, that means that this is going to be 2 times 1. After 1 hour, she will have traveled a total of 2 miles. All right, I got that. Now let me go back to this. I was kind of a chicken. Let me see. I got to take the number of minutes or hours. Half an hour, that's 30 minutes. So do I do 2 times 30? No way, man. I'm going to do 2 times a half. I'm going to do a fraction because I ain't afraid to know fraction. Let me see. 2 times a half. What's a half of 2? That's 1. So after half an hour, she's traveled 1 mile. Let's go back to this one. This time she walks, this is not 25 minutes, folks. Not 25 minutes. This is a quarter of an hour. That's 15 minutes. So I'm going to do this. I'm going to take 2 and multiply it by 0.25. Or you could write 1 over 4, whatever you like. Let me see. If I take 2 and multiply it by 0.25, that's going to be equal to, I don't need a calculator. That's going to be exactly half a mile. Let's keep on keeping on. Let me see. To get this one, I'm going to take 2 and multiply it by 1.25. You could use a calculator or not. I'm not. Let me see. After 1, she does 2 and then another quarter. This is going to be 2.5 miles. And then lastly, if I take 2 and multiply it by 1.5, that's going to be equal to 3 miles. This isn't hard, friends. It's not rocket science, but it's the beginning of it. All right, number 8's done. Let's look at number 9. We're going to do something similar. It says, we're stuffing envelopes again? Noah's stuffing envelopes with invitations to the schools. No one cares about the festival. He stuffs 4. Man, my other dude, what was his name? Mario, he's a better worker. This guy only does 4 envelopes every minute. So let's see. The independent quantity this time, again, we got time. The units, it's not hours. He's doing this every minute. A good expression for time, we're going to use that T again. And then for the dependent quantity, like what's changing based off of time? It's the amount of envelopes that he's stuffing. So let me see. The quantity is going to be the envelopes, a good, let me see, I can't spell envelopes, man. Envelopes, a good unit for it. Unit? Did I do something wrong? Expression, let me see. I'm going to skip that for a minute. I guess, let me see, quantity. It's the number of envelopes, the units of the envelopes, man. Am I tripping? I might be. I'm going to skip it for we'll get to it. Expression, let me see. He stuffs 4 envelopes a minute, so the number of envelopes is going to be equal to 4 multiplied by t, where t is time. So let's see. If this guy has been stuffing envelopes for 5 minutes, the number of envelopes he's got is 4 times 5. What's 4 times 5? That's 20. And then the next one, if he's been stuffing envelopes for 10 minutes, again, that's 4 times 10, that's 40. And then 4 times 15, that's the next one. Let me see, the 4 times 15, that's 60, okay. And then 4 times 20, I could do that one. That one's really quick, that's 80. And then 4 times 25, that's my favorite. That's like a C note, that's 100. 100 what? These are envelopes. Spelling, man. All right. Let's go on to the next one. Let's take a look at number 14. It's a new type of problem. It says identify the input value, the output value, and the rate of change for each function. The input value, that is the amount that we're going to be, let me see. Let me just read this. It says, Owen is riding his bike to his friend's house at a rate of 6 miles per hour. The function d of t equals 6t represents the distance Owen rides as a function of time. Now I know what they're talking about. I hope you noticed that when I first read it, I kind of stuttered. I didn't know what they were talking about when they said, what's the input value? Given this function, d of t is equal to 6t. T is the input. That's what's going to go into the function. And what's going to come out of it is distance. This is my output value. Now, the rate of change, let's read this again. Owen is riding his bike to his friend's house at a rate of 6 miles per hour. Every hour, he's going up by 6 miles. So the rate of change is this guy. Now, let's talk about this guy for a minute, the rate of change. This function, it's written in slope-intercept form. Typically, when it's in slope-intercept form, most of you guys know that it's y equals mx plus b. This value is a rate of change. It's always being multiplied to our variable. In this problem, the variable is t, and then what's our b value? There is no b value. What does that mean? Oh, that means that the b value is 0. So let's see if we could figure this out. We got to figure out what the input value is. I already said that the input value is t. The output value is the distance, and the distance is equal to 6t. So the output is going to be 6t. What's our rate of change? I already specified the rate of change in this problem, the rate of change. And we could kind of see it from the story. The rate of change is 6, because after every 1 hour, he's going to go up 6 miles for that 1 hour. One more thing to notice about the rate of change. We always want to write that how much it's changing for every 1 unit of time that's going by. So after every 1 hour, he's going up 6 miles. So the rate of change is 6. Let's take a look at number 15. I got to go over to the back side of this thing. Hold on. All right, here we go. We got this. You got me, camera? Okay. Yep. It says, Rochelle. She is shopping for earrings, and each pair of earrings costs $15. The function C of E. What the heck is C? Oh, the cost, and E is earrings. Okay, the cost for every set of earrings is 15 times E. That must mean that each set of earrings costs $15. This represents the total cost of the earrings. All right, so let's see if we could get this. Depending on the number of earrings, we're going to have an associated cost. So the input value is going to be the number of earrings. The output value is going to be the total cost. I'm just going to write cost. So let's see. Based off of I got to go back because I forgot what the instructions were. I think they wanted to know what the input value was, and it was earrings. We're going to associate that with the variable E. The output is the cost. We're going to associate that with the variable C. And then the cost, it's equal to $15 multiplied by E. So this is going to be our output value. This is our input value, output value. They want to know what the rate of change is. Let me give you 3 seconds to figure out what the rate of change is. I'll give you 3 seconds. 3, psych, the rate of change is 15. Sorry, y'all, I need to go. I got time for you, but we got to keep on pressing on. Man, these are my favorite. This is the easiest thing ever. Let's take a look at this. I'm excited about this. For some of you little honey bears that love to do your multiplication, this is your time to shine. It says right here, solve each function for the given input value. The function a of t equals 7 times t. Represents the total amount of money in dollars Carmen earns babysitting as a function of time. And that's a lot of reading, man. Let me see. This represents the amount of money that she makes for babysitting. How much money does she make babysitting? She makes $7 for every hour. So let me see. If she's babysitting for 3 hours, how much money is she gonna make? Man, that's 7 times 3, that's 21 bucks. What if she's babysitting for 2 hours? Then the function is gonna be 7 times 2. And what's that? 14, that's right. What the heck is that? 14. And then let's do this one. For every not for every 5 hours. If she's been babysitting for 5 hours, that means she will have made a total of 35 bucks. You guys could finish the rest of these. I'm on to the very last problem, everyone. Let's take a look at the back. This was problems 2021 in section 2.1. Let's move on over to problems number 25 and 26. In this problem set, it says use a graph to determine the input value for each given output